so let's go back up here to the top for these blanks. If the values of a function are the same for each given interval of the domain, the function is said to be periodic. Okay, something that is periodic repeats itself. Okay, so if you have periodic mood swings, means you've got a mood swing coming every little bit, right? If you have lots of different things that could fit this category. Periodic means that it's repetitive. The length of the interval that is repeated is called the period of the graph. So, for example, on the graph of sine, right here, what I'm going to do is I'm going to start at the origin, and I'm just going to highlight this graph until it starts to repeat itself. So, right here I go back to the origin. I'm back to where I started, but I'm not doing the same thing I was doing again, right? So, we still haven't got back to the point where we're repeating. But right here, I'm going to start to go up, and then back down, and up, and back down. So, for this graph, the length of that section is your period. And we started at 0, we went to 2 pi, so the period is 2 pi. Now, that should make sense, because where did we get these values from? Well, you got them from the unit circle, right? And on that unit circle, what's going to happen once we get all the way around the circle to 2 pi? We start over, right? We're going to have those same values over and over and over again. So, so for sine, it should make sense that the period of the graph is 2 pi, because 2 pi is a full revolution. We also could do this in degrees. So we could say the period is 360 degrees as well. However, you are more likely to see questions that ask you about this in radians, so we're mostly going to stick with that. So the period of the graph is 2 pi for this. Our domain are possible x values. Do we have any issues with our domain here? Do we have any asymptotes, jumps, anything where we can't put a number in? We do not. This is a continuous graph that just keeps on going forever and ever and ever and ever. So your domain is all real numbers or negative infinity to positive infinity. Now our range, on the other hand, is going to be restricted. What's the very lowest we're ever going to have for this graph? -1. Should I use a parentheses or a bracket with this? Okay, bracket, does it actually ever equal -1? It does, right? It equals -1. So I'm going to include that, and then that'll go up to +1. Okay, so this is your graph of sine. You need to be very familiar with it. Let's go down and look at cosine. Okay, so for cosine, you may have gotten to various points on this as well, so I'm going to give you a couple seconds here. Your table should be 1, 0, -1, 0, 1, 0, -1, 0, 1. And your points, when you graph them, should look like this. I'm going to go ahead and draw in my line now. And it should look like this. So I'm going to give you a second if you need to do that. Okay, so the period of this graph, if we did that same thing, if we started at 0 and we trace this, we would be back up to that maximum point at 2 pi. Then it would start to repeat. Again, this also comes from the unit circle. It should make sense that that is going to be 2 pi. Domain is the same. All real numbers or negative infinity to infinity. Range is also the same, negative 1 to 1. Now, would you guys agree? These basically look like the same graph. Like, pretty close, right? There's, especially like, if you're looking at these from far away, you'll be like, oh, that's a sine or a cosine graph, but it won't be really easy to tell which one is which, right? What is the main difference between these two graphs? Okay, so where it hits that y-axis, its y-intercept, is basically our main difference, right? Because we could take sine, and if we just slid it over a little bit, it would look exactly like cosine. Or if we could take cosine and slide it over a little bit, they'd line up on top of each other. So, whenever you are looking at these graphs, your sine is going to have a y-intercept at the origin. Cosine is going to have a y-intercept at that maximum point, right? That's your difference. It's going to continue to follow that same pattern, right? So you're going from 0, 1, 0, negative 1, 0, 1, 0, negative 1. Same thing over here. You're just starting at a different value. 1, 0, negative 1, 0, 1, 0, negative 1, 0. So knowing those differences in those y-intercepts will help you be able to tell between which graphs are sine and which ones are cosine. For that. All right, so this is really important for us to know because we need to know what the parent graph looks like. What we're going to look at now are all of the transformations that can occur to this graph. So, let me give you this set of notes here. And let me pull this up. Why is it not an option? Oh, there it is. Okay. The good news is you really should already know most of this stuff because transformations, moving something up, down, left, right, shrinking, stretching, it works the same for sine and cosine graphs as it does all the other graphs. So we have already been over a lot of this for the other graphs. The difference is there's going to be a little bit different terminology that we use for these graphs than we do the other graphs. Okay, so some of the things are going to have different names. So let's talk first about translations. So translations is sliding a graph up, down, left, right. So Smith, if we looked at this first example here, it's not a sine graph, but if I'm just looking at x squared plus 3, what has happened to that quadratic graph? Up 3. So this is a quadratic up 3. This is a vertical shift, right? Up or down. And in this particular case, it's up because it's positive. Okay. Monica, for the second one, we're looking at a cubic. What has happened to that cubic? Right 5. This is a horizontal shift. All right, so for the most part, everything works the same. For our trig functions, we're just going to have a few different pieces of terminology we need to know. So, vertical shifts So a vertical shift, if I had f of x equals sine of x plus 1, this would be the sine function translated up 1 unit. So it still does the same thing that it does whenever you graph with others. But what we're going to have to know about here, the terminology we need to know, is where our midline is at. So the midline is the horizontal line that passes through the middle of the graph. And specifically, that's halfway between your max and minimum points, right? So that graph that we just graphed, f of x equals sine x, that graph we just graphed on the last little paper that I gave you, where is the midline for just sine of x, basic sine of x? Okay, it is what equals 0? Y equals 0 is the equation of that line, which is also just called the x-axis. So it's pretty simple what's going to happen for this. Your midline begins at the x-axis for a sine function. If you shift a function up, it's going to move the midline up. If you shift it down, it's going to move the midline down. Like for example, sine of x plus 1, your midline for this would be y equals 1. It's going to be y equals because it's y equals gives us a horizontal line. Midline is pretty simple to find, and it's not really going to get any more complicated than that. That vertical shift on the end is going to give you your midline every time. Okay, questions? All right, horizontal shifts can be complicated or they can be easy. We're going to look at the easy version right now. Then we're going to look at what the complicated version looks like towards the end of these notes. That's why you got this asterisk right here. So, f of x equals cosine of x plus pi. This would be the cosine function shifted to the left pi units. Okay? So, for trig functions, we call a horizontal shift a phase shift. And so if you think of that word phase, like particularly I think of like phases of the moon, they just like circle right back around, right? You go through the whole cycle for the phases of the moon, and then you're back to, you got your full moon all the way to your no moon at all, back to your full moon, back to no moon at all. So it just keeps going around. So this phase shift is your left or right shift, okay? If it is very straightforward, like this, x plus pi, it just is going to be shifted left or right. A note here, we will learn one more thing about horizontal shifts at the end of this section. There is an extra thing we've got to learn. It's really not anything different than regular functions. It's just that I never made you do what we've got to do with regular functions. But we have to be able to do it with trig functions. It doesn't come up a lot with regular functions, but it does with these. So, there is another thing we have to learn about that, but that's as far as we're going to go for this moment. Okay. All right, expansions and compressions. All right, so I always thought these were the more difficult. I don't know why on these notes that I made those bottom two negative. Just let's make them positive. What do negatives do to graphs? They flip them. They do not expand or compress. They flip. So that would be a different conversation. Same thing still happens. Negatives on the outside flip upside down. Negatives on the inside flip left or right. But we're not worried about those right for this moment. So let's see how good we are. This first one right here, this is the absolute value. Liam, what type of compression or expansion do I have there? Vertical? Expansion or compression? Expansion by what factor? By a factor of 3. Okay. Vertical because it's on the outside. Expansion because it's a big number, something bigger than 1. And then we just use that number as our factor. Okay. Troy, the second one. This is also absolute value. What type of expansion or compression do we have there? Good. By what factor? Very good. All right. Abby, for the third one, we've got a quadratic there. What has happened to it? It is not. It is on the inside of the parentheses. So if it did not have those parentheses there, it would be a vertical expansion. It is horizontal compression. So everything on the inside is always backwards. So we've got a big number there, bigger than 1, which actually makes it smaller, which compresses. So anything on the inside is always horizontal. It's either a horizontal stretch or shrink, or it moves it horizontally, left or right, if you're adding or subtracting. And it goes the opposite direction, right? So if you have a big number, it makes it smaller. It also means my factor here is not going to be 2. What's the factor going to be? 1/2. We got to do 1 over 2 for that. And so, Connor, for our last one, this one is also a quadratic. Horizontal expansion. By what factor? It's not 0.5. It's not just 5. It's 2. How'd you get that, Monica? Okay, that's equal to 1/2. So it's 1 divided by 1/2, right? Which we just talked about this with our trig functions. That just flips it, right? If we do 1 divided by something, it just flips it, which gives you a 2. There. So I think expansions and compressions, especially with other functions, are the most difficult to deal with. However, with trig functions, at least these vertical expansions are going to be super duper easy. Okay, they're going to be ones you're going to be able to find really easily. So, the vertical expansion is going to stretch it out taller or shorter. So, whenever we, like if I skip over here to Desmos real quick, let's look at what happens because we can see Desmos. We'll do y equals a sine x right here, add a slider for sine. All right, there's my sine graph. If I make a bigger, see how it makes the waves taller. If I make a smaller, then it makes them shorter. If I go over here, it flips it upside down because it goes to a negative. What this is going to change, a part that we're going to be really interested in for this is called the amplitude. The amplitude is the vertical distance from the midline to a maximum point. Or I could have said minimum point. It doesn't matter. The midline should be in the middle, so that should be the same distance. So it's the vertical distance from the midline to the highest point, or from the midline to the lowest point. Amplitude is super easy to find because it is just that factor of your vertical expansion or compression. So if I have y equals a sine x, then absolute value of a is the amplitude. Notice right there I've got absolute value bars. Why? What do absolute value bars do? Always positive. This tells us amplitude is always positive. So I should have put an example here, like let's say that is a negative 130, right? The negative, just like when we're doing vertical expansions and compressions, the negative flips. It does not change amplitude, it flips the graph. So the amplitude would still be positive for that. So amplitude is going to be one that's super easy to find. If I have y equals 3 sine x, my amplitude would just be 3. It's just that factor out front. For the second one here, my amplitude would be 1/2. And for that last one, my amplitude would be 130. And it would be positive 130 even if I had a negative there, because amplitude is always positive. Okay, the horizontal expansion or compression is going to be a little bit trickier. Let's go back to Desmos real quick. It's not super tricky, but it's not quite as simple as amplitude. If I go back to Desmos real quick, I'm going to take away this A out front here, get rid of that, and I'm going to put a B right here, and I'm actually going to adjust this. Let's go from 0 to 5 and 0.1. Okay. All right. So this right here is just sine of x, our normal graph for sine of x. Watch what happens if I make my b bigger. Okay. If I make my b bigger, it is squashing that graph in this way like an accordion, right? It's like pushing an accordion in. If I make my b smaller, it stretches it out like an accordion. So this is your horizontal stretch and shrink. What that's going to affect about our sine graph, the part that we really care about, is this is going to affect the period of the graph, right? If I go back where sine is just 1, you guys need to know this right here. You'll be able to use Desmos on some things, but not all. But for Desmos, if you're in radians, if you go over here to the wrench, and it should already be in radian mode, if you go to your x-axis and you tell it, you could tell it like, you could do negative pi to pi, and if you tell it to do your step is like pi over 4, or something like that, it will label it in pi's instead of numbers, which may be more helpful to you. Even though I might should have done from negative pi to 2 pi. So you can see what the graph would look like here, and it'll put pi's on the x-axis. So you can see if I increase my b to 2, the period of this graph, how long it takes to repeat, is no longer 2 pi, right? In fact, how long does it take this to start to repeat? We start here, and we go up, back down. We're back to the x-axis, but we still got to do the bottom half of this graph. Right here, we're going to start to repeat, right? So that was from 0 to pi, so we have a period of pi for that. So the way that this is going to work, well, first of all, period is the length of the interval where or let's see, the length of the interval before the function starts to repeat. Before the function starts to repeat. So, what do we say the period of sine and cosine normally is? It's 2 pi, right? So, normal period with no change would be 2 pi. So, when we have a horizontal compression by a factor of something, it is going to change that period by that factor, right? And for our horizontal compression or expansion factor, that was 1 over whatever number was right here beside of our x, right? So if we took 2 pi and multiplied it by our factor, which would be 1 over b, we would get 2 pi divided by b. So the period for any sine or cosine graph is going to be 2 pi divided by b, where b is this number that's multiplied by your x. So, if we look at these examples that I have here, I've got sine of 5 pi. Normal period for sine would be 2 pi. I would divide by that number in front of my x. So 2 pi over 5 would be my period for that first example. For my second example, I would have 2 pi over 1/2. Okay, now we don't like to leave it like that because that is a complex fraction. So dividing fractions is easy as pi. Flip the second and multiply. We will get 4 pi for our period there. And what you should see for that is that if we put a big number on the inside, that is a horizontal compression, right? Big numbers compress on the inside. Everything's backwards. So if we have a horizontal compression, we should see our period being less than 2 pi, which 2 pi divided by 5 would be less than 2 pi. If we have an expansion, so we have a number between 0 and 1, that is a horizontal expansion, we should get a period that is bigger than 2 pi, which is what we see happening here. Okay? We all right here? Okay. So, this is what I had put the asterisk about. If you have a period change and a phase shift, then that's going to make it a little bit more complicated to find your phase shift. What I did with all of our other problems whenever we had to do this is I just avoided ever running into this. I never gave you any problems where you had a B and a C right here. So I just never gave you y equals 2x plus 7 to the second power. So that is why it seems like we haven't done this before, because I just didn't mess with it. You don't see it happen a whole lot, and usually if we understand the other basics, we're good. But with trig functions, it is going to happen a lot. So it's something we have to be able to consider. So if y equals sine of bx plus c, so we have a number here that is that changes our period. That's our horizontal expansion or compression. And we have a number here shifting it left or right, then that is going to be a little bit different. So rather than this just shifting to the left c, it's going to be a phase shift of c divided by b. Okay, so what that'll look like here for this first example, it asks for period and phase shift. So the period we find just like we did before. It is 2 pi divided by the b value, which is this number right here, which is 2. So that will, as our b, that will give us just pi. Okay. Phase shift does not affect the period. The period's found the same way every time. But period does affect phase shift. So your phase shift I have this plus pi on the end, which would make me think to the left pi. But because I also have that period change there, I've got to do left pi over 2. So it's got to be C, this value here, over B. Still opposite direction, so if you have a plus, it'll be to the left. If you have a minus, it'll be to the right. Okay, does this make sense? All right. For the next one, my period is just going to be 2 pi divided by the b value. So 2 pi divided by 1/3. Dividing fractions is easy as pie. I'm going to flip the second and multiply. So I'll get 6 pi. So that will be my period. My phase shift would be still to the left. It's going to be left 9 divided by the b value, which is 1/3. So 9 times 3 over 1 would give me 27. So to the left, 27. Okay, questions here? Okay, so let's summarize here. To me, this is one of the most helpful slides in all of these notes, the one you might want to refer back to the most whenever you're doing your problems that go with this. So the period for sine and cosine, and it does not matter whether it's sine or cosine, this will hold true for either one. It will change what the graph looks like a little bit, but period, amplitude, midline, phase shift, they're all going to be the same. So period of these graphs is going to be 2 pi divided by b. So b is the number multiplied by your x or your theta there. Okay. Amplitude is always just a. Actually, I should say absolute value of a. If a happens to be negative, then it's going to be a positive. Midline is always y equals d, which is just that number added to the end that shifts it up or down. And your phase shift is going to be C over B. And I'm going to put a negative there to remind us it goes in the opposite direction. So one of the big things we're going to have to be able to do is to be able to tell period, amplitude, midline, and phase shift just from an equation. And then eventually from a graph and stuff as well. So let's do a few examples here. First of all, I'm going to actually change my directions here. Instead of vertical shift, let's say midline. Okay, you will always have a period, you will always have an amplitude, you will always have a midline. Those should always have answers, even if it's not been shifted at all. You'll always have those. Phase shift is the only one you will ever say, no, that just doesn't happen for these. Okay, so if I look at number 1, my amplitude comes from the number in front of my sine or cosine, which is 3. So my amplitude would be 3 here. There are not parentheses around this x, which means that the parentheses would just be around that x. So my period of this graph, I don't have a number in front of my x, so it would just be 2 pi. I could put divided by 1 if I want, but we know 2 pi divided by 1 just equals 2 pi. So if you don't have a period change, 2 pi is your answer. You're not going to say none there. There's always a period. It's just going to be 2 pi if it hasn't changed at all. For phase shift, here we are going to say none. This is not shifted to the left or the right any. And our midline is just going to be y equals 4. Okay, questions? All right, so for number 2, let's see. Lennon, what would my amplitude be for number 2? 1/2, perfect. Let's see, Lee, what about the period? 2 pi. Very good, we don't have any changes there. See, Smith, what about a phase shift? Right, very good. +3 or right 3. Very good. Some worksheets will use a plus or a minus to indicate right or left. Sometimes they'll use the words. Either one's fine. And then, midline. Now, I'm inclined to put none here, but I just told you have to have a midline. What is the midline? Y equals 0. Because this has not been shifted up or down any, which means its midline is still the x-axis, which is y equals 0. The only thing you can put none for is phase shift. You will always have amplitude, period, and midline. All right, let's try a couple more that have a little bit more complicated things going on here. Let's see, Maggie, what's our amplitude for number 3? 2. Very good. Alexa, what about our period? Our normal period, just pi, very good. Normal period is 2 pi. We divide by this number right here in front of our x, and that gives us just pi, perfect. Phase shift. Somebody want to try this one? This one's one of those more difficult phase shifts. What is it, Liam? It'll be left 2. And to get that 2, we are doing 4 divided by 2. So our C value right here is 4. Our B value is 2. So 4 divided by 2 gives us 2 for that. There's a lot of 2's in this problem. And then our midline. See, Troy, what's the midline going to be for this one? Y equals 0. We don't have a number added or subtracted to the end, so it's just a 0 for that. Okay, 4 has a little bit of a trick to it. There is no amplitude number there. What's the amplitude going to be? It's going to be 1. Because you can put a 1 right there in front. And we know, like a basic sine graph, highest you have is +1, lowest you have is -1 for that. Our period for this one would be 2 pi divided by 3. Phase shift. What do you think, Connor? This one. It's going to be 3. How are you getting 3? Okay, 2, right. I thought you might be doing it right and just dividing wrong. So we're doing 6 divided by 3, which is 2. There. And then, Gabby, what's our midline for that one? Y equals 4. Very good. Okay, questions? Okay, we are not going to do this part right here. We're going to do that tomorrow. You won't need it for your homework. Let's see. All right, so you got 2 things for homework. You got the practice quiz. You have a delta math. Let's look at that delta math real quick. And just run through, because sometimes okay. Some of these are going to give these to you from a graph instead of the actual equation. So if they give, oh wait, that's the wrong thing. I didn't mean to do that. Okay. If they give you this and ask for amplitude, midline, you're going to figure out where that would be. That'd go right through the middle. Midline to the highest value, that would be 3 for this one. So you just put in 3. So you're pulling out that information that you know. Why is it not letting me type? Okay, it's like I've turned on something that I don't want on. Oh, great. Okay. All right, now I've got it. So it'll look like this. These are going to be the more difficult ones that you have. Let me go through how to do these with you. So pay close attention. These are usually the ones that students have trouble with. So it lets you set your X and Y label. So for these, you're going to have ones with amplitude and period changes. So for this one, my amplitude right here is 7. My period is 2 pi divided by 4, which reduces to pi over 2. So this is what, let's see if I can remember, pi over 2 and that's not really what okay, reset that, okay. Alright, let's do pi over 2 here. I'm just going to go up by 1 here. Okay. Alright, so what you're going to do is it gives you this x-axis label. It's at pi over 2. Put that on your 4th dot. Okay? If you put it on the 4th dot, and the reason we're doing 4 dots is because, like, you got sort of 4 quadrants of the unit circle. Whatever your period is, put it here for your 4th dot. Okay. Then it's going to ask you to move the x-axis scale in place and plot 5 points. So this we're going to put on our 4th dot. And then this one is sine. So sine's y-intercept starts at the midline. Then instead of going up to 1, like our normal sine graph does, we have an amplitude of 7. So we're going to go up to 7. We'll go back to the midline. We'll go down to -7. And then we'll go back to that point. It's going to graph this little section of the graph. All right. So you should go midline, maximum, midline, minimum. Midline, maximum, midline, minimum. Right. And if you put this on the 4th dot, it'll do it correctly. Now, you could spread it on out further if you want, as long as you're going by increments. But if you put it on the 4th dot every time, it should work. So then, if you submit your answer, we've got that one right. So that one is going to be one of the more difficult ones. Right here, this sometimes gives students a little bit of trouble. Right here, the way they have written this. This asks for period, right here. What number is multiplied by our x? No. It's 6/5. So they have put the x in the top of that fraction, but 6/5 times x is the same as 6x over 5. Because that x, if we made it a fraction, it'd be x over 1, and then we'd multiply straight across. So if you see that variable in the numerator of a fraction, you're using that whole fraction as your b value. So your b is 6/5 here. So you would do 2 pi divided by 6/5, 2 pi times 5 over 6, which will give you 10 pi over 6, you want to reduce that to 5 pi over 3. And so you could do 5 pi over 3. And I think that, just to do one more of these so you guys are with me. Period for this one would just be 2 pi because you don't have a number, a b value. Oh, can't just type pi. 2 pi. And then I'm just going to have this go up by 1. Unless you have a really big amplitude, you should just be able to go by 1. Done. All right. So you're going to take 2 pi, you're going to drag it over to the 4th line. All right. This is sine. Sine starts at the midline. We got an amplitude of 3, so instead of going up to 1, we're going to go up to 3. Back down to the midline. Minimum back here. And it'll graph it for you. Those are the ones that students usually have trouble with. If you can get the mechanics of those down, usually this is not a difficult assignment for everybody, but I do remember that being one that we had a little trouble with last time. I think that should pretty much cover what you're going to be asked. Some of them may ask you like a midline or other stuff. I think you'll be fine with that.